I represent one atom, maybe I'll be hydrogen, and Dave represents another atom, he'll be oxygen, and the both of us decide that we want these two electrons, and we're attracted to them because at our core, in this case it's not a heart, but a bunch of protons. And protons are positively charged, and the electrons are negatively charged. Right? So the positive charge protons are pulling on those electrons, and this would be, what Dave and I are doing now is a covalent bond because we're sharing them equally. We both got two hands on them. They're about equal distance from two of us. This is like a bond between carbon and hydrogen. The electrons are shared almost exactly equally. Well done, David. Okay? So a good example of a nearly pure covalent bond. Carbon bonded to hydrogen. So it's carbon, hydrogen. To be a little bit more chemical about it, we can put the two electrons between them, and hydrogen wants those electrons, and carbon, among the other things it's doing, wants those electrons as well. And so they're both equally sharing those electrons. It's almost equally shared. The carbon takes a little bit more because, of course, it's got 6 protons, and hydrogen only has the 1. But still, it's just about equally shared because carbon's 6 protons are shielded by 2 electrons. So it's just about equally shared. You don't need to know about the shielding or anything. You just need to remember that a carbon-hydrogen bond is almost a nearly pure covalent bond, nearly exactly equally shared. But hydrogen does not have the privilege of only being bonded to carbon. We have what we call a polar covalent bond, and that's unequally sharing. And a good example of that is the oxygen and hydrogen bond. A very good example of that. So oxygen, despite of what else it's got going on, it's got other things going on besides bonding to the hydrogen, but it's got 2 bonds. In this case, the poor hydrogen barely hangs on to the electrons, and the oxygen has drawn those electrons into its orbit. So let me try to draw this even more unequal. So here's oxygen. It's got lots of electrons already, but it's a hog. And it pulls those 2 electrons nice and close. The hydrogen barely manages to hang on to those 2 electrons. The oxygen, on the other hand, has them all drawn in nice and close. That's what we call a polar covalent bond because it's polarized. When we say we have a polarized debate, what do we have, Renil?
Very two-sided.
Exactly. So we use the word polar to describe these kinds of bonds as well because they are two-sided. Poor hydrogen doesn't get much of the electrons. I've drawn a really weak circle here for hydrogen. And the electrons are far away from it, quite literally. The electron density is far away from the hydrogen. So in this case, the bully is going to be David. And so this is the polar covalent bond. There's those 2 electrons. Hydrogen's just trying to grab onto them, but oxygen's got them nice and close. Okay? And the hydrogen is at a greater distance from the electron, and there's not much electron density associated with the hydrogen. Okay?
Okay, that's a bad view. She's just putting the water bottle.
Okay. All right. So what's the effect of this polar covalent bond? Well, there's 2 effects. Number 1, the oxygen ends up with an increased electron density. So it's more negative close to the oxygen because it stole 2 electrons that it should have just been sharing. What's the effect on the hydrogen? The hydrogen ends up being positive. Right? It's positive because it should have had 2 electrons to kind of balance its charge, but it doesn't. They're not being shared, they're being shared unequally. So the result of this polar covalent bond is a slight negative charge with the hog, the bully partner, and a slight positive charge with the victim. So the bully tends to get more electrons, and the victim tends to get less electrons. Question? Was it a good one?
Well, Neil didn't think so.
I did.
Which is why he's the bully partner.
See, my original joke had the oxygen as like the dirty capitalist, and the H as like
subsistence farmer.
Yeah. and then of which I said Bernie Sanders could fix that inequality. I found it funny.
I don't know any chemical analogy for that. There is no fix for the inequality, but it does lead to some interesting effects, including life. So yeah, maybe maybe the answer is bigger. So all along this molecule, these molecules that have these hydroxide groups, this hydrogen bond to oxygen, all along this molecule, you'll see this unequal sharing occurring. Well, take a look at your carboxylic acid that makes part of the amino acid. We have our nascent polypeptide, right? And remember, polypeptide has a carbon-carbon nitrogen backbone. So carbon, carbon, nitrogen, and it goes on and on and on and on and on like that. Okay? This is our central carbon. What do we have attached to our central carbon from our amino acids? Dave?
R group.
We have an R group. That's the other group. Good. What else have we got?
Just on the central C?
Yeah, this is the central carbon of our amino acid. Actually, we should... Oh, so you know what? I'm going to put this here. Just so we can get the carbons in a nice row. So this is a central carbon, and this is our central carbon here. And they are chiral, so that little thing goes well. And then this would be another carbon here, and so on. Oh, so we got a number of amino acids in a row. This would be an in here. Okay, we go N to C. So I've drawn this carbon backbone in the direction that the amino acid is actually made, and in the direction we read the amino acid, the polypeptide's made. All right, so this is our central carbon. We've already identified that it's attached to an R group, and we're going to find out what else is attached to it. We've already put that up. A hydrogen is attached. Excellent. So there's a hydrogen attached down there. What else is attached to it?
No H.
Sorry?
Nothing on that one, but on the end there's 2 carbon.
Yeah, we got.
I mean,
so there's an amino
sorry,
group here.
That's what I meant, not carbon. I meant
Okay.
hydrogen.
There's an amino group here, and what do we got here?
2 oxygens and
That's right.
nitrogen.
And
COOH.
nope, we're satisfied.
No, that's it, yeah.
Okay. And so we've got another hydrogen there, and on we go. Okay. All right. So this is our polypeptide. We've noticed that we have R groups all on one side, and it turns out that the protein molecule, the new polypeptide, kind of does make sure that the R groups are all on one side. Okay? So the molecule just kind of lines itself up so that we get R groups on one side of the molecule. We tend to get R groups on one side. The molecule isn't a straight line, but the R groups all tend to point out the same way. Question? Yes?
So you have the carbon with the 2 oxygen.
Yes?
And then to its right you have the nitrogen.
Yes?
Would that not have 2 hydrogen?
Nitrogen can only form a total of 3 bonds. So it's going to use 1 bond to form to the main carbon. It used to have 2 hydrogens before it was put into a polypeptide, and it had a dehydration synthesis in which it grabbed the OH from the carboxyl group that was on the other side of the next amino acid. So this is another central carbon here. So there's our R group, and we're on this end, the C side of the amino acid. This is how it used to be. And then the amino acid next to it had a nitrogen, and you were right, nitrogen forms 3 bonds. This is the next amino acid along. Okay? This is our first amino acid. This is our central carbon, so on the C side it's called a carboxyl group. This is the next amino acid coming along. On its N side, it's got this amine group. And then how this whole molecule is put together was this. Water was pulled out by a dehydration synthesis, and that left us with this. Okay? So do you see nitrogen still has 3 bonds?
Yeah.
But one of them used to be at a hydrogen, but that was contributed to the water, and that water is pulled out and the 2 ends have joined together. And that's how a peptide is made. Does that make sense now?
Yeah.
Good. So, where are we going with this? So there's only 1 nitrogen here. Now, nitrogen is another bully as well too. Not only is oxygen a bully, nitrogen is a bully as well too. So it pulls electrons towards it as well too. So here's another place where we have what kind of bond? A? A?
Peptide.
Well, yes, it is a peptide bond, but we're talking about this bond here.
Polar.
It's a polar covalent bond. Okay, so we have all these places where we have hydrogens, and those hydrogens are attached to, the correct word for them, Steve kept saying, it's electronegative. That's the word. I don't know if you have to know that word for biology. Or not from Mr. J. No, so you don't have to word no electronegative. That's our explanation as to why they're bullies. We say they have a high electron negativity. It isn't really an explanation, it's just giving a name to it, isn't it? Right? But that's what we say. Oh, it has a high electron negativity, therefore if it pulls the electron density towards it. Okay?
What causes a high electron?
It's because the combination of the shielding and the
Number of protons.
effective charge when the shielding is counted for. So the effective charge of an oxygen is greater than the effective charge of a hydrogen because of the number of protons.
But it was like
There's a little formula for it too. You put in the number of shells and electrons, you subtract them, and you get the effective charge.
the ratio of like the number of protons to the number of shells it has.
Yeah, it's the number of protons it has, less kind of the shielding effect. And the shielding effect isn't 100%, right? It's a reduced 100%, and that gives you the effective charge, and that's what we use to calculate the electron negativity. Where are we going with this? Oh, so what we see is all along this molecule are going to be these lonely hydrogens. Why do I say lonely? Because their electron density has been pulled away. Okay? So we can get a polar covalent bond with oxygen and hydrogen. We can also get a polar covalent bond with nitrogen and hydrogen. It's another polar covalent bond. Hydrogen is always the loser in polar covalent bonds. Hydrogen is always the loser. And nitrogen pulls the electron density away. So we have essentially an electropositive hydrogen, a hydrogen that's got too much positive charge because it has no electrons to kind of help balance that charge. And we have the element next to it that's got a little too much negative charge. Okay? So, where does the bonding occur? Well, the bonding occurs between that hydrogen who goes looking in the molecule for free electrons that it can kind of mooch off of. Where, along this molecule, do you think the best case of free electrons to mooch off of is?
Best to mooch off of? Does carbon have?
Where along this molecule, so these hydrogens here, they're looking for free electrons to mooch off of, right? They don't have enough electrons. They still have a positive charge. They're looking for somebody with a lot of electrons they can go mooch off with. Where on this molecule do we see a species that's going to have a lot of electrons they can mooch off with? The carbons. Why do you think the carbons might have a lot of electrons to mooch off of?
Because carbons have lots of bonds.
Okay, but if they have lots of bonds, what does that mean that they're doing?
They like giving away.
They're sharing lots. So do they have a lot? No, they're sharing, right? That means they only really have 4 when you get down to it, because they're always sharing. And carbon, is carbon one of these things that shares unequally? No, carbon tends to share equally. So we're not going to find free electrons around the carbon. Right? All of its electrons are accounted for in bonds. They're already being shared. Remember this case where David was bullying me, and I'm looking for free electrons? I'm not going to go look for carbon because carbon's already equally sharing. It's not going to help. Where do I see something with free electrons? Got lots, not free, but lots of electrons. Somewhere I can mooch off of the negative charge. This oxygen. Why is this oxygen going to be electron rich? Could be a little nest of negative charge.
Because it's a hog.
It's a hog. It's attached to carbon, and we already know that carbon isn't a hog. Right? Carbon shares equally with hydrogen, so it can't be that much stronger than hydrogen. So this carbon actually is going to be a little bit positive, isn't it? Right? Because it's attached to a hog, not once, but twice. And what else do we know from our grade 9 or grade 11 chemistry about this oxygen that doesn't even show up on this diagram?
It has
8 electrons.
It has extra electrons there, right? Octet has 8 electrons around it. It's 4 it's pretending to share with the carbon, and then 4 more that are just, it's all its own. It is an electron-rich species. Where is this hydrogen going to be attracted? Oxygen. Now, can it get to this oxygen? And I'll help you out with that. No, it can't bend to get there. Picture Picture this as this brush as the bond between the two carbons, and then picture the oxygen and the hydrogen as being on either side of the brush. They can't get at each other. You see that? If this brush represents this bond, and this represents the hydrogen and the oxygen, they can't get at each other. They just can't. They can't twist around to get at each other. Where can that hydrogen get at? Another one. How far? It just out of the blue. How far along do you think it goes before it can get that molecule to twist around so it can link up?
The one on the other eye.
It's about 3 along. So it manages to twist the molecule, this one here, manages to twist the molecule so about 3 amino acids along, it bonds to that oxygen. It's about 3 amino acids along. Not the next one, not the next one, but the one after that, it can grab onto.
Is that what forms the pentagon shape?
And that's not what the pentagon shape, that is the helix.
Yeah.
Okay? So, what you should picture is you know those? Picture a whole bunch of segments. Like I've got board pins, and each segment represents a bond, right? This is the backbone of the molecule, right? Carbon, carbon, nitrogen, carbon, carbon, nitrogen. They got a whole bunch of board pins, okay? So they're twisting around to try to get to each other. It's 3 sets later before that hydrogen manages to twist around and bond or be attracted to that oxygen. That forces the molecule to circle in on itself. And that's where you get your alpha helix. Okay? The alpha helix forms on its own. There's no enzymatic action that helps the alpha helix form. Just as the protein is produced, the hydrogen is sitting there looking for something, and it sees that amino acid, 3 residues along, and it goes and it bonds to it. And then another one is produced, and the molecule twists on itself as that hydrogen goes looking for something that's a source of electrons, and it grabs onto it. So literally, it's like making shavings. You know when you like shave ice cream? Like, you know, and it just twists in on itself? That's exactly what it's like when the protein molecule is made. The protein molecule is made, it comes out like an ice cream scoop, and it twists in on itself and grabs on via the hydrogen to the, what's called the carbonyl oxygen. The hydrogen grabs onto 1,3 though along, so it'd be this hydrogen here that would manage to grab onto this one over here. Okay? It grabs onto that one, and then that twists the molecule into a helical shape. The molecule twists in a helical shape with the backbone on the inside. And what do you think, by lucky accident, ends up pointing outwards as the molecule builds itself?
The hydrogen.
The
Oxygens?
well,
remainders.
think about it. You've got this tube that's made from this protein molecule cycling back on itself as those hydrogens look for places to grab on. What do you think points outwards? And what do you think points outwards? This is the backbone. What do you think ends up pointing outwards as that molecule twists among itself?
The R groups.
The R groups point outwards. Why? I say happy accident. I say happy accident. Why happy accident? That the R groups point outwards.
Anyways.
What's the whole point of this thing?
R groups.
That's right. The R groups determine what this protein does, what it's good for. You want them outwards. If they were inwards, all proteins would be the same. You wouldn't have different proteins for collagen in your skin, or to make your hair, or to make a digestive enzyme. The R groups have to point outwards so they can do whatever it is that they're supposed to do. If they pointed inwards, the molecule would, all protein molecules would be the same. There'd be no point in making any different proteins. And the proteins wouldn't have any function because they would just be a spiral of hydrogen sticking out at you. Right? Useless. The R groups point outwards as the helix goes. All right, good. The team is recognizing that you should write that down. So what are the key things I've just covered? There are polar covalent bonds in the backbone of the polypeptide. So there are polar covalent bonds in the backbone of the polypeptide. This backbone, that's carbon, carbon, nitrogen, carbon, carbon, nitrogen. The nitrogen has a hydrogen attached to it, and the electron density is closer to the nitrogen. The long shot, the upshot of that, the whole point is that you get a polar covalent bond where the hydrogen experiences a slight positive charge because its electrons are being stolen, hogged, by the nitrogen. This hydrogen would very much like to have some electrons to balance that positive charge because its electrons that it tried to share of nitrogen are partially stolen by the nitrogen. How can it balance that charge? It looks to get close to something with a strong negative charge. And on this backbone, we see that these carbonyl carbons have this oxygen attached to them that is electron rich. It's full of electrons because it's grabbed the electrons it's sharing with carbon. Plus, it has 4 more electrons it's not sharing with anybody. The hydrogen sees that as a knot of negative charge and it's attracted to it. This partial bond where the positive hydrogen is attracted to this negative charge is called a... What do you think it might be called? A hydrogen bond.
Wow.
That's what a hydrogen bond is.
You did
It's hydrogen looking for something negative because it's had its electrons pulled away. And it makes a partial bond. It's a weak bond because the electrons are still unequally shared. Oxygen doesn't let go of them, but the hydrogen gets to hang out right next to it. Yes? Yeah, they are weak because there's no actual sharing. Because once again, oxygen doesn't share. We know that. So even the hydrogen could be right there. Oxygen's still going to keep those 2 electrons really close to it. But the hydrogen's still attracted to it because the hydrogen's positive. It cannot take those electrons from oxygen. And those who are taking chemistry know that there's only one element that can even hope to try to take electrons from oxygen. Every other element gets its electrons stolen by oxygen. Oxygen is so electronegative. Yes?
But
You wouldn't
fluoride.
necessarily call it an ionic bond, right? 'Cause it's
It is not an ionic bond because there is no transfer of electrons. Okay? So there's another type of bond called a dative covalent bond. You've never heard of it? That's okay.
Sounds
So
familiar.
there are, all you need to know for this course is there's pure covalent bonds, and that's important. Pure covalent bond is like one between carbon and hydrogen. It's just almost pure because the electrons are equally shared. The other type of bond you have to know for this course is a polar covalent bond where the electrons are unevenly shared. The hydrogen's still attached, but it's unevenly shared. And that's like oxygen to hydrogen or nitrogen to hydrogen. And now we have a third type of bond, which is a hydrogen bond, which is just then a weak bond. It's just the attraction of that positive hydrogen to the oxygen. And so we
What a great lesson that was.
Yes.
Where you actually the shape comes from the hydrogen on one side being attracted to the oxygen on the other side.
It comes from the hydrogen being attracted to the oxygen 3 residues down. So that bends the molecule so that oxygen attaches. That produces a curve.
This diagram.
Yes.
The oxygen on all 3 sides.
There's free rotation without the bond. These bonds are all free. This bond here is free to rotate. It can twist. One configuration is more stable than others, and it rotates freely once it's made, but the configuration that's most stable is the one where that oxygen is pointing towards that hydrogen. And that just means the molecule curves back to get at the hydrogen. And then that one, the new amino acid will also have an oxygen sticking out. And then there'll be another hydrogen that will curve back, and that twists the molecule because it's always reaching 3 back. It's kind of like you 3 at the table. Right? If I make a long line of students, and this student grabs at every 3rd student, the line will end up curving at that point. Because this student will also grab at the 3rd student along. And of course, you end up spiraling on top of each other, because that's just the geometry of it, right? You can't, if you grab the next person, like you get 2 circles, then you're out of space. You end up stacking on top of each other and up you go.